My name is Son To. I am from New Mexico State University. So today I'm going to talk about a conformant planner with disjunctive representation of belief states. Actually, I don't put the explicit there because I just found that the explicit form is just for the intermediate state, not for the representation. The motivation of the paper is that we observe that there are two mainstream of approaches to the conformant planning problem based on best first search and progression search. There are many state-of-the-art conformant planner follow this approach. For example, PON, CFF, and CPA, and the complete version. We can see that the transition computation in this approach is usually slow, and the memory consumption might be huge. The other approach is approximation. Is the first proposed by Sheng and Barrow in 2001. A belief state is where a belief state is approximated by the intersection of the space inside the belief state. We can see that in this approach, the computation for the successor state is very fast, and it requires very less memory. But unfortunately, it's incomplete. So the motivation here is to establish a bridge between the two approaches. So how? We need to build a conformant planner that has the following property. First, is complete. Second, the representation of belief state is compact. That means actually it's not too big like belief state. Third, the transition computation is relatively simple and efficient. So, for example, given a problem in which the domain contains n propositions, and the initial information is completely unknown. So we can observe that the belief state in this problem, the initial belief state in this problem contains 2 to the n states inside. And on the other hand, we can observe that the belief state is logically equivalent to an empty logical formula like in DNF, CNF, or NNF. So our goal is to find a representation of belief states such that the size of the representation of the initial state in this case is 0 instead of 2 to the n as in the belief state, and the computation of the successor state is fast. So our approach to the conformant planning problem is that we use a DNF, the disjunctive normal formula, in a compact form to represent belief states. And the reason is that the computation is straightforward, easy, and fast, provided that the size of the DNF formula is not too large. So we need to find a transition function that has the following properties. It is able to deal with any equivalent any DNF that is equivalent to the DNF representing a belief state. Therefore, it allows us to use a compact DNF form for representation of belief states. And the second property is that the successor belief state can be computed in polynomial term of the size of the DNF state with feasible assumptions. Third, the representation of successor Billy state is compact, actually relatively compact. And so the question is that how can we compute the successor state given that the representation of the Billy state is in a compact DNF form? Because we know that given a conditional effect, we need to know that whether the condition in the conditional effect is satisfied in the DNF state or not, so that we can take the literal in the effect to the, you can put that to the result of the successor state. But for a compact form, sometimes we don't know that. So to deal with that, we need to first to convert it to an equivalent form that we call is explicit for the with respect to the action. And the point here is we need to minimize the difference between the two formula, but we don't want to change the current representation to another formula that is completely different. So it may take too much computation, and the size of the state may blow up. Second, we compute the successor state based on the explicit formula computed in the first step, and the result is written in a DNF formula. And third, we simplify the result in the DNF formula to an equivalent compact DNF formula form, which we call is minimum, and it will be defined later. So we need some preliminary definitions for our work. If we consider a state as a set of literal, so a partial state delta is a set of state. It's a subset of a state, and a DNF state delta, bit delta, is a disjunctive set of a partial states. A DNF state delta is minimum if it does not contain a pair of partial state delta and delta price, such that one is the superset of the other. So the function min delta return DNF state by removing the superset in the DNF state delta. So for example, if given delta is a set of partial state f and h, not g and h, g and not h, and we can see that min delta is f and h, g and not h, because this state is a subset, superset of this state, so we just remove it. So we can easily see that min delta is minimum and logically equivalent to delta. Now we need to define the explicit form. Given an action A with the conditional effect set CA is psi A to LA for psi I to Li for I equal to 1 to n. So delta is explicit for action A if for every psi I either delta entails phi I or delta entails not psi I host. So intuitively we know that if delta is explicit for A, so for every conditional effect here, we know what's going on in the successor state, because here we the if this whole, so we put it in the successor state. If this not whole, so we just ignore it. So a DNS state bit delta is explicit for a national if for every partial state inside it is explicit for HNA. So now, for example, given delta is a set of two partial states, F and not G, HNA with the set of conditional effects F and G to H and not G to G. Now we need to define delta plus gamma. So intuitively, gamma here is the condition in the conditional effect. So we need to, if we need to decide that if gamma is entailed in delta or gamma, the truth value of gamma in delta is not true. So we just leave return the set of delta here. Otherwise, we extend it to delta to this delta and to the union of delta and gamma, and the other this. And we can easily see that in this case, every this one return also a DNS state, and that every state in this in every state in this DNS state, the truth value of gamma is decidable. For example, now we want to compute this state, this partial state plus this conditional condition of the conditional effect. So we can easily see that it's equal to this. This belongs to the second case. And for example, if we want to compute not G plus this condition here, and it's still not G because the truth value of not G is, sorry, the truth value of F and G is already known in not G here in the state not G. So it belongs to the first case. So we define the bit delta plus gamma. Here, bit delta is a DNF state, not a partial state like this. Just for this one, we just compute every this function from here for every partial state, and then we take the union of them, and then we remove the superset inside the result set. So in this case, we can see that delta plus F and G here is equivalent to union of this set and this set. But after we remove the superset, this superset, we have a F and G here and not G here. We can easily see that delta plus gamma is logically equivalent to delta, and if for two consistent of literal sets gamma 1 and gamma 2, we have that delta plus gamma 1 and then plus gamma 2 equal to delta plus gamma 2 and plus gamma 1. So suppose we have an action A with the conditional effect CA equal to psi I to Li for every I from 1 to n. So the explicit form of delta with respect to A is defined like this. And this one actually we do in in this example, for example. But we repeat it for every condition in the conditional effect set here. So we can see how to compute the result after we test this. And similarly, we define the explicit form of bit delta is like this. We just sum on the condition in the conditional effect of the set CA. And we can see that ESPA of delta is equal to this set. First, we sum delta with the first conditional here, the condition here, first condition in the first conditional effect here, and we have this set like in this result, and then we sum to not go here, and we got the same set. So we can easily see that now in this form. For every conditional psi I in the conditional effect set CA, the truth value of it is known in this. So now we can easily compute the successor state now. And here we the direct effect of an action A in a partial state delta is defined by this formula. This intuitively we take every literal in the right hand side of the conditional effect if the condition is satisfied in the partial state. Then we compute the result of the execution A in partial state delta. And we can see that if we take any literal here, so and if the negation exists in delta, so we should remove it from in the result because we add that literal in this already. And here is now the transition function is defined by this phi DNF of action A in DNF state delta is equivalent to mean of result of every partial state in the explicit form of delta with respect to A if delta entails the precondition of A. Otherwise, it's undefined. So the transition function can be generalized for a sequence of actions like this. So here we introduce some theoretical results. Let delta be a DNF state, and A1 to AN is a sequence of actions. Then phi hat DNF of A1 to AN and DNF state delta is sound and complete with respect to the possible world semantics. And second, given two DNF state delta and delta prime that they are equivalent, then phi hat DNF of the sequence action A1 to AN of delta is equivalent to the phi hat DNF of the sequence action A1 to AN of the delta price. So this implies that we can work with any equivalent DNF state, not only the one particular DNF state that if they are equivalent and represent for a Billy state. So now I'm talking a little bit about the implementation. The DNF is is modified from CPA. We reuse translator of the input theory. So this translator is written in Prolog, and it reads the input of the problem in PDDL, and then translate to another format that DNF and CPA can read. In the implementation, we do the optimization like this. First, we group all the conditional effects with the same antecedent, psi to L1, psi to L2, and so on, and psi to Ln, to one conditional effects, psi to L1 to Ln now. And we just ignore the effects whose heads are already in the state, because the computation, the semantic after the computation doesn't change. And third, the computation of direct effects and computation of the explicit form are carried out together. That we don't do it in two different phases, but we do it interleavely. Since we know that when we compute the explicit form of a DNF state, we already knew that which condition is satisfied in which partial state and which doesn't satisfy in which partial state. So we use that information to compute the effects. We don't. So later we don't need to recompute that again. We use the three heuristics in lexicographical order in our planner. First, we base on the goal satisfied in the DNF state delta. Second, we base on the size of the DNF state delta. And the third one, we compute this square distance from DNF state delta to the goal by this formula. Intuitively, we sum on the square of the distance from the current partial state to the goal, and this one promotes the state that if they have the same value for the first two heuristics, so for the state that they have more state that close to the goal, and so we promote as DNF state. So experimental setup, we compare the performance of DNF with the four state-of-the-art conformant planner. There, first is CPA, the winner in the IPC 2008. Second is T0, I think it's the winner of IPC 2007. And CFF and PON. The benchmark problem was collected from IPC, previous IPC and IPC 2008, and from some challenging problems proposed by the author of T0. And the total number of domains is 17, and the total number of problem instances is 74. And we run the problem in a Linux machine with 2.66 gigahertz and 4 gigabyte memory. And here, for a problem, if the planner run the problem with the least running time and return a solution, we give it 5 points. And for the planner that can solve the second fastest the problem, we give it 4 points, and so on. And if the planner cannot find any solution for the problem, we give it 0 point. And we sum for every problem instances. And here we have the summary number here. So we can see that DNF can speed up very well. And in the second summary chart, we this one shows that DNF can solve the largest instant problem in 7 domains out of 17 domains, such that no other planner can solve that instant problem. And it turned out that T0 can solve the largest instant problem in the domain is forest that no other planner can solve, and no other planners can solve the largest instant problem that the other can solve. And this is the scalability. Here is the number of problems the planner can solve. So DNF can solve almost 69 problems, whether the other can solve less than the problem in the benchmark experiment. We notice the overhead here of the DNF because of the translation process. So the advantage is we give a complete conformant planner with fast computation, and it can enhance scalability. But we will see the problem that the overhead of translation of the input theory is significant, and if the problem require very large size to represent the belief state in DNF formula, so we may have a problem with that. And then later we will work on this. So thank you. What do you mean other problem? Yes. Yes. You mean the domain proposed by T0 author? This is a conformant planning problem. Yes. Yes. We yes, actually, if we compute effective heuristic in conformant planner, it's very, very expensive, I think so. And like CFF, it's very effective. I think the heuristic is much more effective than our heuristic. But unfortunately, it only works in a class of problem, not for many problems. And then for some problem, it turned out that it never can solve, can give any solution. And our heuristic, I know that, but actually it can go for a large class of problem. I mean, it's not so good, but it's acceptable. Not. The heuristic have a lot. If we use another structural heuristic, so we will have some problem. Yes, but I try with some combination of heuristic, and it turned out this heuristic